The setup is shown in the figure was to find the relative atomic mass of M. Okay, there is M here. The electrolysis was carried out for 10 minutes, very good, using a constant current, okay. The mass of the cathode cell in A was increased by 31. So here there is an increasing of 31.75 milligram. And B, the mass of cathode was 147.60. Okay, milligrams. Don't forget these milligrams. Assume that the electrolysis of water does not take place in cells A and B. So basically they say for neglect the electrolysis of water means neglect the oxidation of OH minus to oxygen and reduction of H plus to H2. That is what it means. Identify the anode and cathode of each cells A and B. So you know they have given these terminals, negative and positive. So in electrolysis, as I told you before, in many cases, if the battery is negative in charge, that should be surely the cathode. Right? So here this would be a negative charge part. This would be positive charge. And same place, if this is positive, and this is negative. Okay. So basically, this is our cathode. This is our anode in cell B. And here this is positive anode and this is cathode. Write the half reaction taking place at each electrode in each cell. So if I take this one as cell A, so the oxidation is copper to copper 2 plus, so balance it. Reduction is also copper 2 plus to copper, you need to balance. Okay. In the same way, cell B, anode is 3, so 3 anode oxidation. So this is what you can, this is how you can write down in cell A also. Is the good way. So M to M3 plus, because here you see stoichiometry is 3 here. And in reduction, M3 plus to M solid. So put the physical states, put the electrons, all these are important. So anode reaction is this. Cathode reaction, you can write down 4 cathode reduction is this one. Okay, so that is how you write. That is important to understand the anode and cathode first, then write down the reaction as it is. The next one, calculate the constant current used in the electrolysis. So this is where you need to understand what is actually happening in this entire process. Okay, so you know here in cell A, in the reduction, copper 2 plus is taking 2 electrons and precipitating out as copper solid. Okay, so basically the mass 31.75 grams of magnesium is increased for copper because of the deposition of the copper in cathode. So you can find moles of copper deposited by using this mass 31.75 into 10 to the power minus 3, let's say, to make this in gram, divide by the copper molecular weight. It is 63, I would guess. Second. Okay. Yeah, 63.5 gram per mole. So you can find the number of moles of copper. So you know this one really well. Okay. So if you know this copper number of moles, you can multiply this by 2 to get the amount of electron moles. So you find the amount of electron moles easily. Okay. For an example, here so the number of moles of copper is 5 into 10 to the power minus 4 moles, if I check the answer. So the amount of electron moles that is used is 10 into 10 to the power minus 4 moles. Why? It is the twice. Stoichiometry is 1:2. Then what you have to do here is you need to find the amount of charges that is when through this circuit when these 2 electrons are used per one copper atom. So it is by using Faraday's constant, right? So to get the moles of electron, you need automatically this one per mole, charge per mole, right? So you need to find this by charge per mole. So for that, what we normally do, so we have the number of moles here. This is 10 to the power minus 3. You can multiply this one. So because you know the number of moles of electrons, so you need to know this number of moles of electron, that is 10 to the power minus 3. Then you multiply it by this Faraday's constant, because Faraday's constant means charge per mole. So you know the number of moles, you multiply it by charge per mole, 96,500 in generally. So you will get the amount of charges, which is typically called Q. And you will get this one in Coulomb. So this Coulomb value is 96.5 coulombs. Then the simplest equation, Q is equal to IT. The current I is equal to Q over T, right? So Q, you know, 96.5 coulomb. You need to divide this 96.5 by time. So time is 10 minutes. You convert that into seconds. So it will be 600 seconds and you will get the current. Okay, so the current will be 0.16 ampere. So you need to understand what I did. I did find the number of moles of copper. So they have given the number of moles of copper. Then find the electron moles. So if you know the electron moles, you find the total charge. So if you know the total charge, you can divide it by the time to get the current. So that is very easy. Then the next part is calculate the relative atomic mass of M. So now we have to go in the other way around. Same situation, but in the other way around. Because we know the amount of current passed through this cell A. So the amount of current passed through this cell B also should be same, because same cell. Okay. So you can calculate the charge using those two. So Q is equal to IT. So do you know the current? Yes, that is 0.16. You know the time? Yeah, 10 minutes. So 600 seconds. So you know the charge. Okay. So 0.16 times 600 will be automatically charge is 96.5 coulomb, because the charge also should be same. If the current is same, the time is same. Okay. So you know the charge. Now how can you find the number of moles of charge? So moles of charge, again same story. What is it? 96.5 coulomb divided by Faraday. To get the charge from mole, you multiply. To get the mole from charge, you divide. Okay, so you will get this same amount of things, but you get 10 to the power minus 3 moles. Now you come back to the next reaction, that is M3 plus gets 3 electrons to form M solid, right? So now the stoichiometric ratio is 3:1. So to get the number of moles of M deposited, you need to divide the electron moles by 3. So it is basically 10 to the power minus 3 moles divided by 3. That is the number of moles of this one. Then if you know the number of moles of this one, what is the equation? Mass deposited is equal to moles deposited times the molecular mass. So mass deposited, they have given 147.60 milligram, 60 milligram. Number of moles, you know from here. Then the only thing that you don't know is the capital M. So you can easily find the relative molecular mass or relative atomic mass of M. Okay, so this is very nice question where you use in one way to get the current and the other way to get the molecular weight. Nice. Let's move on to the part B of this one. So A, B, C are coordination compounds. They have an octahedral geometry. Nice. In each compound, two types of ligands are coordinated. The molecular formula is given and they are not in order. And given below are the observations and compounds treated with lead acetate. So this is treated with lead acetate. So we will go through the compounds first. Now think about this compound. So they have nickel, chlorine, hydrogen, nitrogen. First one, okay. I will take one by one. And the other one is nickel, iodide, N4O2, and there is hydrogen as well. I missed that one, 16. Last one, NiCl2, H15, N3O3. So the important thing is they have this is octahedral geometry. So the first point that I am going to make here, around nickel, there should be 6 ligands in each of these compounds. Right? This is first point. Second point here is only 2 types of ligands are formed. So I am going to try to predict what can be these 2 types of ligands. Okay. So here I see Cl2 and NH. So normally the ligands that I normally know here could be like, okay, so nickel could be complex to 2 chlorine. And from N4H12, I can guess this could be NH3 times 4. Just you need to check that. So 4 nitrogen, 4 into 3, 12 hydrogen. Yes, this could be because then I have 4 ligands plus 2 ligands to make this octahedral geometry. This is octahedral geometry. Right? So this is one. And here, if I check this one, again, I have nickel. And I have iodine here. So maybe it could be 2 iodines here. And there are N4O2 and H6. So if I check in a similar way for 4 nitrogen and for this remaining hydrogen to be ammonia. So it could be 4 ammonia. So 4 ammonia means 4 nitrogens are taken. So 12 hydrogens are taken. So the remaining hydrogens are 4 hydrogen and 2 oxygen, which could be 2 water molecules. Nice, right? So this one also could be 2 chlorines. And again, nitrogen, 3 nitrogen. So this could be 3 ammonia, I would guess, because of 3 nitrogen. So that means 9 hydrogens are going from 15. 15 minus 9 is 6. So 6 hydrogen and 3 oxygen would give 3 water. Right? For this one, to make this as an octahedral, 4 ammonia and 2 Cl is used. But for these two, you see here, there are more than 6 ligands. Here there are in fact 8 ligands that can be present. And here there are 8 ligands that can be present. So there are many combinations that can be here in order to have this octahedral geometry, which means 6 ligands. For an example, it could be like nickel and 4 ammonia. Okay, 4 ammonia and 2 water molecules. So this is ammonia here, 4 and 2. So this could form like this. If nickel is 2 plus, so this should be 2 plus because these two are neutral. And here this could be nickel Cl, 2 Cls and 4 ammonias. So if nickel is 2 plus, this is 2 minus, so no charge. And in the same way here, for there will be 6 here to octahedral, to 2 plus, to neutralize this 2 plus, this iodine can be there in the outside like I2. The same way here also, nickel, 3 ammonia, 3 water, and Cl2. But don't forget this, one of the I can be going to inside and one of the ammonia can come outside. One of the I can go inside and one of the water can come outside. So we don't know the exact coordination, which of them are the 6 ligands. But you can think, or maybe like this, or maybe a different one from here. But for this one, surely it should be this, because no other ligands to form the octahedral geometry, the first one. Okay. So that is why here they have given some observation when you add lead acetates in order to determine what it should be. What are these 6 ligands should be? So you see here, when you add A to A, when you add lead acetate, you see a white precipitate is formed. So here only the compound that can form when you add lead acetate is PbCl2 in order to give a white color precipitate. So in order to give this white color precipitate, this chlorine cannot be within this primary coordination sphere. It should be present as a counter ion. Okay, so surely chlorine should be something like this, outside the box, outside the primary coordination sphere. In the second one, they say no precipitate, because no precipitate you see in this first compound, NiCl2H12N4, this one. The 6 ligands are within the primary coordination sphere and this has no charge. So surely this B is this one. And in the same way, C forms a yellow precipitate. So automatically you can understand Pb with iodine will form PBI, which is yellow in color and it is dissolving in hot water. Okay, so automatically you see here, this is related to this one and this chlorinated compound related to A. Okay, so you need to first understand that part. That is very important to understand here. So give the structures of ABC. So surely the structures of ABC should be this one here for this one for B. This one is for A and this one is for C, right? Otherwise, if you put iodine inside or chlorine inside here in the main primary coordination sphere, there will be no precipitate forming these two. This formation of the precipitate indicates that iodine and chlorines are present outside the box as the counter ions, which means to balance these charges. Okay, so that is the way that you predict these things. The chemical formula of the precipitate from on each treatment. So basically the precipitate from is PbCl2 and PbI2. State a chemical test together with the observation to identify each of the anions. Each of the anions, if present, are not coordinated to the metal ion in the compounds given above. So the anions are basically here I minus and Cl minus. So what you can do, you can add silver nitrate, right? Silver nitrate. So when you add silver nitrate, what is going to happen? So I'm going to write this I minus in this side, Cl minus in this side. So what is going to basically happening? AgI and AgCl would form, right? So here AgI will form and here AgCl would form, but both are going to be precipitated. This is yellow, this is white. So how can you identify further? You add this to conc ammonia. So when you add conc ammonia, this will not dissolve and this will dissolve. This is how you can identify. Okay. There are many other ways, but this is the basic way that we identify. Right, moving on. A transition metal M forms a colored complex P, ion P, in aqueous media. So it forms aqueous media. It has the following general formula. So M, H2O, N, M plus. So it undergoes the given reaction. So when P added with aqueous ammonia, a green color precipitate is formed. So normally green color precipitate with ammonia, what it can be? It can be, so when you have like, it can be Fe2 plus forming the ferrous hydroxide, little pale green in color. Then you have nickel 2 plus, which form nickel hydroxide, which is also green in color. So one of these two can be, or even maybe it can be chromium 3 plus, chromic hydroxide, which is dirty green color. So these three can be green color. So excess ammonia gives deep blue color solution. So this finds the dust because this clearly confirms this is nickel amine, hexamine 2 plus, because this is the deep blue color solution that is going to form. And when you add conc HCl, so it will form NiCl4 minus. Identify M, give the oxidation state of M in complex ion P. So this is M is nickel. So what is the oxidation state here? So nickel forms with H2O is 6, 2 plus, right? So N is equal to 6, M is equal to 2. And oxidation state of M is 2 plus 2, okay? Electronic configuration, so these are very simple things you can write down. N is equal to 6, M is equal to 2. Give the geometry of P, so P is octahedral geometry, okay? So you have to give the geometry that is octahedral. Give the structures of QRS, so QRS means what is Q? Yeah, Q is the green color precipitate, so Q is nickel hydroxide. Q is nickel hydroxide. Q is nickel hydroxide. And R is NiCl4 minus. And S is hexamine nickel 2. Okay, so that is the end, I guess. Now give the IUPAC names of P, R, and S. What is P here? So P is hexa aqua nickel 2. Okay, P. Hexa aqua nickel 2. What is R? This one. This one. Tetra chlorido nickelate 2. Okay. And S is this one. This is hexaamine nickel 2. The only difference is here P and S are cation. The charges are positive, so we use nickel. But R is a negative charge species, so we use nickelate. That's the idea. And this is hexa aqua, this is hexaamine, and here this is tetrachlorido, not chloro. Okay, chlorido. That's the new way. Right, so that's it. This is a nice question again.